So we're going to spend the next hour or so talking about service-oriented architecture with SQL Server. Before we get started, if you have any questions, concerns, comments, or anything about this session, any other session, or anything in the future, feel free to contact me at the email or blog site you see on the screen. I'll also put it up at the end of the session as well. So we're going to quickly run through today a quick look at SOA architecture and what's involved. And then we're going to talk about two primary technologies in SQL Server 2005 and beyond that help you integrate with an SOA architecture in your solutions. So service-oriented architecture, many of you probably already know or have worked with it in the past, but it basically involves loosely coupled services or applications that interface together across a disconnected link. Could be synchronous or asynchronous in nature. The two primary technologies we're going to talk about today with SQL Server are web services and spend more time on message queuing. Web services in SQL Server basically provide a direct web service endpoint in your existing SQL Server infrastructure today. SQL 2005 included this in the RTM version. SQL 2008 will also include it. We're not going to spend a lot of time talking about it today because in SQL 2008 the feature is actually deprecated in favor of WCF, which many of you may be aware of. But basically web services give you a way to provide interoperability across either different platforms or across geographic segments. And they communicate in a variety of ways, one of which is SOAP, which is the way that the feature that SQL Server implements. So in terms of SQL Server, native HTTP support in 2005 can expose any of your SQL modules, stored procedures or functions, and you can also actually expose batch or ad hoc statements. It's recommended not to do that because of the security impact, but it is possible. And SQL Server maintains all of your security aspects, so any security that you're used to working with today in SQL Server is exactly what you would be working with in terms of securing your HTTP endpoint. So why was HTTP support embedded in SQL 2005? Heterogeneous data access. So it's becoming more and more prevalent for enterprise architectures to include a mix of not only hardware and platforms such as Unix, Linux, Apple, and Windows platforms, but also a variety of development platforms such as Java, PHP, Perl, and of course your Microsoft Stack and .NET. So using an HTTP endpoint in SQL 2005 and beyond can give you the ability to natively interact with SQL Server without using like a third-party driver or plugin like you might do today. For example, if you use Linux front-end servers to connect to a SQL Server backend or something of that nature. You can limit your security exposure on your outer perimeter. If you have web servers in your DMZ or on your internet-facing layer, you can continue to leverage simple port 80 firewall holes instead of having it opening on 1443 or some other port that you have your SQL Server instance listening on. And the architecture in SQL Server actually does not require IIS. So if any of you attended my SQL 2008 presentation yesterday, you realize that in SQL 2008 you can actually run reporting services without IIS. In SQL 2005, there's a few things you can do that you couldn't do prior to SQL 2005 without IIS as well. One of those is HTTP endpoint. The way this is built is it's on top of the HTTP sys driver that's included in Windows 2003 SP1 and beyond. So obviously a requirement if you don't want to use IIS would be to be running on a platform of Server 2003 SP1 or later. Basically in your SQL Server, we'll run through a demo in a bit, but basically all you do is reserve an endpoint on a port and a namespace through the HTTP sys driver. And then SQL Server provides built-in WSDLs. You have the options to customize those, but it has built-in WSDLs based on the stored procedures or functions that you expose as web service methods over that endpoint. Okay, so that's about web services in a nutshell with SQL Server. And now we're going to move on to messaging or asynchronous message processing in SQL Server. So one of the most anticipated and heavily used features with SQL 2005 was a feature called Service Broker. And basically what Service Broker is a reliable messaging platform embedded into your SQL Server database engine. So if any of you have ever worked with something like IBM Q Series or MSMQ or any messaging technology that's out there today, Service Broker is the exact same technology embedded into SQL Server natively. Some of the advantages you can see on screen. It's built into the database engine. It's a first-class object. So all of your management, all of your security, all of your disaster recovery planning, all of your programming skills that you're used to working with today in terms of T-SQL are what you would leverage to work with Service Broker in SQL Server 2005 and beyond. So you wouldn't have to learn any new technology. You wouldn't have to stand up any additional infrastructure to support, for example, an MSMQ server or an IBM Q Series server. The big paradigm shift in terms of Service Broker being embedded in a SQL Server for most database programmers is really a new thinking, because database programming up until Service Broker was all synchronous. You'd submit a request, wait for a response, and get the response back, and then act on that response. So you'd run a query and act on the data. You'd alter a table and wait for that to commit, and then continue on. Service Broker is a fully asynchronous technology. Very similar semantics to your T-SQL, the types of DML you write today in terms of selecting and inserting or updating, only it's fully asynchronous as opposed to send the response and wait for the response to return. You basically send the request goes off and does its work when it deems appropriate based on how you configured it, and then a response comes back later that you can then act on when it comes back or just disregard entirely. So the big thing is that everything is in the database. We talked about this briefly, but all your data, all your messaging, all your logic, all the security is fully embedded and baked into SQL Server. All your management in terms of moving databases, backup, restore, all fully embedded. And it also integrates fully with all the tools that you're used to working with today in terms of Management Studio, Configuration Manager, etc. So some of the basic concepts you'd have to get used to for working with Service Broker in SQL Server would be some of the things you won't see on screen. So a service is basically what you interact with. Think of that as, in a web services model, what the actual service that you would connect to and try to execute methods on or what have you. A queue is actually the physical storage. Think of this as similar to a table. You can actually query it just like a table in terms of selecting. You cannot insert, update, and delete from a queue. You do that through Service Broker DML, which I'll show you in a bit. A conversation, which is a two-way dialogue between two people. The best example or way I can think of explaining this is think of what you do when you stick a letter in the mail. You drop off a packet of data, which is your letter that you've written enclosed in an envelope. The postal service or whoever takes it and delivers it to its destination. That person opens up, reads the letter, writes some sort of response, sticks it in the post office box on their end, and it comes back. Obviously, you don't stand at the post office, for 2 days or however long waiting for that letter to come back. You go off and do other things, come back a few days later, check your mail. Oh, you've got the response, and you read it and go from there. The conversation, think of that as the post office. Actually, the delivery of the message back and forth between you and the person you're speaking with. And of course, a message would be similar to, it's basically a data packet. So let's look at some of the architecture points with Service Broker and some of the features. Messages are guaranteed to be delivered once and in the correct order. So if you send a message, it's guaranteed to be delivered one time and only one time. You don't want to obviously get into one problem with messaging platforms is building logic in to ensure that you don't process duplicate messages or duplicate data packets. Service Broker bakes that functionality in for you. The order you send a message in is guaranteed to be the order that it arrives at the destination. If you send 3 messages, the first message will arrive before the second will arrive before the third, and then finally the third would arrive. You can relate messages using what are called conversation groups. So for example, if you have a process, think of a travel agency. If you go to book a trip, you might have to book a hotel, a flight, and a rental car. Okay? Those could be 3 separate services. You know, you need to book a rental car with the rental agency, you need to book a flight with your airline, and you need to book a hotel with your hotel at the destination. All 3 of those messages could go to either the same system, they could go to 3 separate systems that are separated by wide geographic links. But you might want to coordinate those messages together so that you don't send a response back to the user saying your itinerary is complete when you haven't received the response from, for example, the hotel or the airline and only the rental car. Likewise, you also might not want to mix processing of that request with other requests, other travel requests. So that ability is baked in as well. Asynchronous delivery. So if you're sending data across multiple instances of SQL Server, could be multiple instances on the same server, or it could be multiple instances on different servers that are in the same room or across the world. It's all asynchronous delivery using queuing concepts. And we'll walk through that a bit in some demos. You've got a wide variety of scheduling and processing flexibility. You can schedule processing on demand. You can schedule processing on a schedule. You can schedule processing as data arrives. And we'll walk through what's referred to as activation and how that is baked into the SQL Server instances as well. Like I just mentioned, automatic service activation. So basically, you can program either in T-SQL or in an external .NET app, automatic response or activation to messages as they arrive on the queue. So if nothing gets delivered to a queue for an hour, there's no reason to keep your .NET service active or some stored procedure loaded into memory. That stored procedure will be disconnected. A message arrives, it'll be automatically spun up to process data that is arriving on the queue. I'll also show you how that can be throttled either up or down based on whether you want to process 4 threads at a time, 8 threads at a time, 2, et cetera, et cetera. And of course, as we mentioned, full database integration. Service brokering is fully transactional in terms of if you send a message, and you receive a successful response to that send, and your database suddenly goes corrupt or goes offline, or you lose a drive or whatever, what have you. That message is fully baked into the transaction log, just like you're working with database tables are today, so inserts, updates, deletes. And security, there's multiple layers of security, multiple types of security. You can use domain authentication, Windows authentication in multiple different models. You can use certificate authentication for secure delivery of messages across multiple domains that perhaps don't trust each other, or across non-Windows domains, for example. We'll walk through that briefly as well. So we talked a bit about a few of the key models. The way these are physically implemented are through some of the things you see on screen. A message type is just a user-defined text of data saying that this message is of type A. So go back to the airline example. You might have an airline message, an airline reservation message, a hotel reservation message type, and a rental car reservation type. A contract is optional. It basically defines a guaranteed way of communicating between 2 services. I can send this message type, you can send that message type. I can only send it to you, you can't send it to me, or vice versa. Fully customizable. We talked about a queue and a service. A dialogue is basically what wraps your conversation. This is the single most fine-grained level of communication between two remote services. You start up a dialogue, and that's what you send you send conversations across. Routing, which we're going to talk about, one of the key features and abilities with Service Broker and SQL Server is the ability to scale out instead of scale up. So if you have an airline reservation system like we talked about earlier, and suddenly people start using your system, millions and millions of people across the world, and you hadn't planned for it. Well, instead of buying bigger hardware for your reservation system, the whole concept is add another box beside it, or 10 other boxes beside it, and have your web servers communicate with any of those 10 that expose that service or that functionality, as opposed to having your standard monolithic big server sitting in your back room like you do today if you were using your standard database communication like inserts, updates, deletes. And we'll walk through a routing example as well. So let's take a quick high-level overview of how a single interaction between two services would occur. So basically what we have here is our user sitting at their laptop, and what we're going to mimic here is an employee submitting an expense report. Okay, so they get all these receipts, they got to fill out their expense report. So they go onto their tool and they fill out their expense report with multiple line items. And what they do is they say, okay, I'm done, and they hit submit. In your typical database world, what you would do is execute a stored procedure that might have a variety of parameters or an XML parameter or something that kind of wraps all the information up in it. In this case, they're still going to submit that stored procedure. However, what that stored procedure is going to do is instead of inserting data into a table or validating the data while the person is waiting online, it's going to take that data packet and basically push it onto a queue. Okay, so it's going to take that message, push it onto what we're calling the expense queue in this example, and immediately at this point return control to the user. So as far as the user is concerned, that expense report has been submitted for processing, and they'll be notified via email or something later that it's been processed and accepted or rejected, and they have to fix it. In the background, what's going to happen is this instance on the left is going to start a dialogue or a conversation with the instance on your right. Okay, because the instance on your right is actually the back-end system that processes and validates the expense report. The system on your left is just a web server that accepts web service requests from this application on your laptop. Okay, now remember, again, this is all in the background. The user's already off doing other things. So once that dialogue is set up and that message is actually passed across to the right side, or to the processing server, that processing server now is going to, again, relinquish control to the service on your left. The service on your left is now going to continue on doing other things while the server on your right is processing this expense report. So that message arrives on the queue on this instance on your right, and activation has been set up to fire up this stored procedure called process expenses. So that process expense stored procedure is going to be spun up, and what it's going to do is pull that message off the queue and process it. Okay, so it's going to shred that message packet. It's going to do some validation, make sure they didn't exceed their limits, and they have the appropriate receipts or what have you, whatever is going to be done. And then it's going to either accept or reject that expense report. Okay, and let's say it accepts it, so it inserts an expense report record and some line item details, and it would send back an accepted response. If it was rejected for whatever reason, it could formulate a response that said it was rejected for these reasons, or these line items were out of order, or what have you. Once that's done, it's going to basically send a message back to the initiating service on your left, asynchronously again. So that process expense report is done, and it's generated accept or reject message, and it's now sent that message back to the initiator. At that point, again, in the background, that message will be sent across the same dialogue back to the initiating service on your left, where that message will arrive on the queue, and again, another stored procedure that's set up to be activated when a message arrives will be spun up and say, hey, this expense report from so-and-so was accepted, send them an email. Or this expense report was rejected for whatever reason, send them an email with a link telling them to go fix it and submit it again. And that's basically the end of the process there. So that's a high-level overview. Now we've talked about activation a bit. Activation comes in two flavors. One which is called internal activation, which is basically baked into the database engine, and as messages arrive on a queue, a stored procedure would be fired to handle that data as it's arriving. This is not a trigger. It would be, I guess, a way to look at it would be maybe an asynchronous trigger, but triggers are transactionally scoped, meaning if you insert into a table that fires a trigger, whatever happens in that trigger is going to fire in the same transactional context that insert fired in. So if you did a rollback, anything in a trigger would be rolled back along with whatever fired the trigger. If, in this case, you can't, somebody that submits an expense report or a stored procedure is fired up, this is in a totally separate transaction context from whatever sent the data packet, okay? You can specify, you have the ability to say, I want 1 or 2 or 3 or 4, or how many ever threads to process data as it arrives. That gives you the ability to throttle your resource utilization. So the way this would work conceptually is we have our target queue here. So think of this as your table. This is your physical storage. Messages begin to arrive on this queue. Okay, so a stored procedure is fired up to process messages. And it starts pulling those messages off the queue and actually doing whatever it needs to do to process them. As more messages arrive, that procedure continues to try to process them. If messages are arriving faster than that single stored procedure can process them, and you've specified that you want multiple procedures to be activated if necessary, a second procedure would be fired up to start processing messages as well. And then both of these guys would be processing messages at the same time concurrently, in parallel. And that would continue to scale until it reached whatever number of threads you had specified to process. The second form of activation is external activation. And what this is you build a .NET component of your own that runs possibly as a service or whatever to actually process messages that arrive on the queue. The slight difference with this is it's not fully baked in and automatic. You have to write some logic in your .NET code to subscribe to messages or to subscribe to events that will fire from that queue and say, hey, you need to process messages now, they're arriving. And you also need to include handling to say, as I'm processing messages, if I get an event that says, messages are arriving faster than you can process them, you would have to write multi-threaded code to actually spawn off another thread to actually process additional messages if you so chose. Okay, there's some samples with this, both out on the web and also shipped with SQL Server as a built-in sample. So we talked about conversation group locking, meaning you can group multiple messages together. Again, go back to the airline or the travel reservation system I was telling you about. The way that works is a dialogue is started. Let's say this is a single person saying, I want to book this reservation. Okay, when that stored procedure pulls that message off, that dialogue is locked by that stored procedure. Okay, meaning if another message arrives on that queue from the same dialogue, so in the case of the travel reservation, 3 messages might arrive. 1 for an airline, 1 for a rental car, and 1 for a hotel. What conversation group locking gives you the ability to do is to make sure that all messages from that same dialogue can't be processed by another queue reader. So if another queue reader spawns up and tries to pull messages off this queue that you see here, it won't be allowed to pull any messages off because that dialog 1 is locked by the first queue reader, and there's no other messages for it to process. Now, if messages arrive from another dialog, another person perhaps trying to reserve travel, that queue reader would be allowed to pull off for a separate conversation group. Okay, so let's briefly look at some of the security architecture. You've got multiple options for securing message delivery in SQL Server. And they're basically, the transport security and the dialogue security are 2 very similar things in nature. They both give you the ability to lock messages down using keys of a variety of algorithms at a variety of strengths. The difference being that the biggest difference between the 2 modes of security, which you can use together, you can use them both at the same time. And the broker engine is actually smart enough to dual encrypt data. So if you set up both, just for as a belts and suspenders kind of thing. The service broker engine is smart enough to actually not dual encrypt messages if you've got both types of security configured. The biggest difference between the two is that transport security is point-to-point, meaning if you have instance A and instance B, transport security will take care of securing data between those two instances. However, if instance B receives a message and then continues to forward it on to another instance using either message forwarding or just another form of coding that basically receives messages and sends them to another instance, the communication between instance B and instance C, for example, would not be guaranteed by transport security. Obviously, you could set up transport security between instance B and C, but those two instances might be out of your control. If you're in an enterprise where you have multiple systems and multiple groups, all administered by multiple DBAs, they might not set up transport security and they might be vulnerable there. Dialog security, on the other hand, is end-to-end, meaning that message is encrypted until it reaches its final destination where something has been given a key that will unlock it and allow you to process it. So in the case where you have multiple levels or multiple layers of instances that message might traverse, dialog security is probably your better option. I like to put this slide up just to show an additional feature, so to speak, of Service Broker and SQL Server. And it really gets to separation of duties. So you have developers and you have administrators. And what Microsoft tries to do is separate the duties as much as possible. The code in this case would be begin dialog and send messages and what have you. Administrators are responsible for administrating the instances, securing the boxes, disaster recovery planning, et cetera, et cetera. If in developer's code you send a message and you specify that you want encryption to be off, that doesn't mean that encryption is guaranteed to not occur. What it means is encryption is optional. So if the administrators on the back end have set up these queues or these instances to communicate in a secure way, those messages will be encrypted and secured. If they haven't, those messages will not be encrypted and secured. However, if your developers code delivery of messages saying encryption equals on, that means encryption is required. So if the back-end administrators haven't configured secure communications between the two instances, then those messages will not even be able to be delivered. Okay, so encryption equals on really means encryption is required. Encryption off really means encryption is optional. So let's talk about routing for a minute. So you use routing to basically route messages that have been delivered to a particular service to a physical machine or a physical instance. You can specify multiple routes for the same service. That gives you the ability to scale out. So if you have a travel service like I mentioned earlier, and developers write code to say send this message to the travel service, that travel service could be backed by 15 instances running on 15 different physical servers. The way that the front-end web server knows where to send those messages is based on what you've specified for routing. In this case, you would have specified perhaps 15 different routes to 15 different servers. And it's a load balancing scenario. It's not a broadcasting scenario. So it would be delivered to one of the 15 back-end servers. Okay, so it's a load balancing scale-out scenario, and it's all TCP communications. You also have the ability to do dynamic routing, where instead of having to have those routes pre-configured on every web server, saying, hey, this travel service can be delivered to any of these 15 locations, you can set up a dynamic routing service whereby those front-end web servers will ping what's referred to as this dynamic routing service instance for where those messages can be delivered to. And that all happens dynamically as routes are expired from your web server. So to walk through a couple simple routing scenarios, a simple one-to-one scenario where you have service A on the left and service C on the right. Server A and server C, where server C exposes a service B, apparently on the right. Server A tries to deliver a message to service B. It will scan its routing table, which is basically configured in a routing table stored in your local SQL Server, which might be an Express instance. for where it needs to deliver a message to service B. It'll find that route, service B down here, and it'll actually deliver to that machine. Okay? On the destination side, or on your server C over there on the right, it scans through its routing table to make sure that it actually exposes that service. And if it finds that that instance exposes that service, it'll accept that message and process it. The message will be delivered to one of those 3 servers. Okay? Again, it will scan to make sure it exposes that service, and it'll process the message. Forwarding. So you also have the ability to have what are referred to, or what in concept are called forwarders, meaning just a hopping point, so to speak, along your path to your final destination. You might use this in scale-out scenarios where you have thousands and thousands of front-end servers that need to deliver data to a single back-end server. Obviously, you probably won't be able to have hundreds of thousands of web servers all connect to a single back-end server at the same time. So you could funnel those through an additional layer of maybe hundreds of web servers in the middle, or app servers in the middle. Basically, the concept here is that the initial instance on your left has a route to the forwarder, so it delivers its message to the forwarder. The forwarder has a route to service B, which is exposed on that physical server C on the back end. It will deliver that message on to server C, where it will again scan to see if it exposes that service and process it. And again, this is just another extension of the forwarders, meaning you can have multiple layers of forwarders. You're not limited to having a single layer of forwarders or layers between your final backend system. You could actually scale this up to 15, 20, 100, thousands of layers if you so chose. One thing that usually comes to people's minds when I start showing these slides here are licensing costs. Service Broker is fully embedded in Express. And Express, as you know, is free, so your licensing costs are relatively low there. The only limitation to the licensing with SQL Express is that somewhere along the path of delivery, it has to touch a fully licensed version of SQL Server. That could be a Workgroup edition, a Standard edition, or an Enterprise edition, any of the 3. So you could have 15,000 Express instances that are front-end web servers and a second layer perhaps that all deliver to one single Workgroup instance on the back end, and you're fully covered in terms of licensing. So classification, basically classification is just the process of how the initiating instance determines which machine or which route to pick. What happens is as messages are delivered, they go through a classifying function to determine where that particular message should be delivered. Okay, so as you try to send on a queue, it'll be popped onto a local queue initially, and then it'll be run through a classifier function to determine, hey, where do I need to send this? In the scenario where you have static route set up, it'll just pick one of the n number of routes that you have specified. They're sticky in terms of if you have the same client sending multiple messages, it'll be sticky to the route that was picked for the first one. And also obviously make sure that that particular receiving service is still responding. The dynamic routing scenario that I was telling you about is if you try to send a message, at the time that that classifier fires up to try to determine where that message should be delivered, it won't find anything in the routing table. It'll say, hey, I don't know where I should send this, but I know that I've been configured to ping a dynamic routing service to determine where I should send this. So it'll deliver a message off to this BCN service is what it's referred to say, hey, where should I send this? That service then delivers a message to say, hey, add this to your routing table. A route will be added. The classifier will then know, hey, okay, I need to send this to address X, and off the message will go. So some simple interaction. There are some slight differences between using Service Broker on a local instance of SQL Server or across multiple instances. The biggest difference is that on a local instance, as you send messages, they will be delivered directly to the target queue. So if you have multiple databases on a single SQL Server instance where you're trying to deliver messages between the two databases asynchronously, as you send messages, those messages will be delivered directly into the receiving queue. They won't traverse anything else. as opposed to if you're traversing instances, could be multiple instances on the same server or on disparate servers. Another queue is introduced referred to as the transmission queue. You can see it right here in the middle of your screen. Every server that uses Service Broker will have a transmission queue. And what that is a temporary holding place for message packets that need to be delivered outside that local instance. That provides you that asynchronous capability. So if you try to send to a service that's remote and you don't want to wait on the wire for that remote service to be contacted and that message to obviously be delivered, that kind of defeats the purpose of asynchronous processing. That message will be popped onto a local queue referred to as a transmission queue, and it'll wait there for background threads to actually spawn up and deliver it to the remote instance. So wrapping up here before we get into some demos, recommended uses of Service Broker and SQL Server, asynchronous database work. This could be logging. This could be triggers that could fire asynchronously outside of the transactional context of what's happening. Your classic OLTP scenarios, which we'll talk about here in a minute. Scaling out of services, batch streaming, that gets into things like logging. If you just need to log auditing or logging information or things that are occurring. And back-end services, which are like we just talked about with the travel service. So some examples of some asynchronous database work could be asynchronous triggers, like I mentioned. You can use Service Broker to govern processing. So for example, if you have thousands and thousands of clients submitting work to be processed, if you were trying to do that all synchronously and online, you don't have much control over your resource consumption. Whereas if instead of that, they switch to an asynchronous model where they just submit work requests to be processed as they can be, you can govern, you can use that max queue reader setting to govern how much resources are going to be dedicated to processing those. Your classical OLTP scenarios are the funneling type scenarios where you have thousands and thousands of front-end machines that could be front-end web servers that are handling requests from people. Think of this as like flight reservation systems where you have hundreds and hundreds and thousands of airports in the world that each have hundreds of kiosks that people are trying to either reserve, get their tickets or going to something like Expedia.com or someplace like that and try to reserve. So you have thousands and thousands and thousands of these front-end machines that need to communicate with one or tens of back-end machines. You can't have hundreds of thousands of front-end machines all connect to a single back-end system. It's just unfeasible. So the classic OLTP approach is to funnel those through layers of machines. So hundreds of thousands of machines to thousands of machines to tens of machines. That's where the forwarding type functionality would come in handy. We've talked about the scale out capabilities where you have a single initiator communicating with multiple destination services. Your classic one-way scenarios, which you can think of as logging scenarios. If you need to audit today, if you need to audit your SQL Server systems, you probably have a variety of things, one of which might be triggers that fire as people read or write data to a table. You could convert those to be asynchronous, lower your resource utilization on your box, and increase your throughput or your response time to your end users. Because those triggers can be processed, the logging and whatnot can be processed out of band. And we've used this scenario throughout the day, so I'll use it here. If you think of, again, a travel booking scenario where you have a client communicating with a single travel service that might be actually backed by 3 separate services in the back end, some different ways that you could configure this on the back end are to have all 4 of those services on a single SQL instance. That's great for small to medium-sized businesses that don't have a lot of volume. As you start increasing your volume, you can segment 1 or more of those onto a separate SQL instance and have 1 or more of them hosted on another separate instance. As you start to get more volume, maybe you need to separate all of them onto multiple individual SQL instances. And as you get really big, you might need to have each one of those single services hosted on multiple servers. So you might have multiple servers processing your flight reservations, multiple servers processing your car reservations, and multiple servers processing your hotel reservations. You would do that using partition services or replicating of data, or just your simple scale-out scenarios. This next slide is to show that Service Broker is fully supported in any type of high availability scenario you can think of. Clustering, log shipping, mirroring, backup restore, replication, et cetera, all fully supported. Okay, so before we jump into some demos here, do we have any questions that I can answer? I don't see any. So let's go. How are we doing on time? Where are my time guys? I'm sorry? 20 minutes? Good. I lost my time guys. Might end up keeping you guys here forever. Okay. So let's start with just some basic overviews. So what I'm going to do here is mimic a scenario where I have a grocery store or something of that nature, and I want to keep track of my inventory. So what I'm going to do here is create an inventory database to use. The first thing I'm going to do is create an endpoint. So endpoints are just physical network locations that information can be sent and received across in SQL Server. In this case, I'm going to create an endpoint, you can see here, for use with Service Broker. And I'm going to use Windows authentication. I'm saying encryption is supported. And here's the port I'm going to use. I'm going to use port 4022 for this particular instance. I'm going to create that instance. I'm going to use my inventory database. Now what I'm going to do is create some logical message types. And all these are, again, are user-defined identifiers for the types of data you're passing back and forth. I'm going to use two message types here, an inventory update message type and an inventory update response message type. What these will be, as you can probably figure out, is one will be to mimic basically somebody at a cash register taking an order. Somebody bought this item. I need to update my inventory on my back-end system to say, you know, now somebody has sold one of these, so you need to decrement your inventory. The inventory update response will be the back-end server sending a response to the cash register system or the front-end system saying, okay, I got your inventory update. Here's the new inventory levels, you know, which might be totally different from one less than what it was before because you might have hundreds and hundreds of cash registers, obviously. The next thing I'm going to do is create a contract. So we talked about a contract. This is optional, but I'm going to use it here for demo purposes. And you can see what I'm going to do is specify that the inventory update message types can only be sent by the initiator of the conversation. This would be your cash register system, for example. The inventory update response can only be sent by the target being your back-end, you know, system that keeps track of inventory levels across your entire enterprise. So a simple contract. Next, I'm going to create the queue, which is the physical storage for where this information lives. Now, what I'm going to do here for this first demo is I'm going to have all my systems or all my queues and service hosted in a single database. Okay, so I'm going to have my client and my server all hosted in the same database. This is just for simplicity's sake. These could both be hosted on separate servers or what have you. I don't have multiple machines here. I do have multiple instances that we'll use in a minute. So what I'm going to do is the first one I'm going to create is my client queue. So this is the queue that's going to store data that is delivered from or delivered back to my client. And then I'm going to do the same thing, and I'm going to create, before I create my server queue, the next thing I'm going to create is my service. So I'm going to create a client service. You can see here I'm going to specify that that service is going to use that inventory client queue as its physical storage location. And this here is saying that this service has to conform to this contract. That's the contract that we created above. Okay? Now I'm going to do the same thing, only instead of for the client objects, I'm going to create the server objects. So the server needs a queue as well, and the server needs a service. And it's the same name, only instead of server, service inventory client, it's service inventory server. It's using its own queue, and it's using the same contract. So it has to abide by that same contract as the client. So let's take a look at some of the metadata. This is just showing what we have on my system. You can see the two message types. These message types up here are system defaults. These are the two message types I created. You can see here's a contract, that I had created. You can see here are the two queues, here's the two services. And just to show you that you can actually query your queues, you can see what I'm going to do here is actually select from my server queue and select from my client queue. So you can run select statements against your queues just like you can against tables. And we'll do that here throughout. Now the next thing I'm going to do is just create a simple table called my inventory table. It would contain a title, a quantity. So the title is, you can see maybe an item number, an inventory number, and the quantity is how many of those that I have here at my client. I'm just going to create a few of them, all with a quantity of 200. And we'll take a quick look. You can see I have all these 18 products that I have 200 of. So now let's start working with what you would do with Service Broker. So here I am, let's pretend I'm the client, I'm a cash register. I'm a cash register. And somebody comes along and buys a product. And what it looks like here is that they're buying the PS1372 product. So what I'm going to do is I'm going to send a message to my back-end server saying that somebody bought this, and they actually bought, it looks like 197 of them because I'm saying that the new quantity is 3. I think that's what I'm doing. So what I'm going to be doing here is starting a conversation. So here's that dialogue conversation that we talked about at the beginning. I'm going to say that I'm coming from my client service. I'm delivering this information to my server service. I'm using this contract. And my encryption I'm saying off. Now again, remember that doesn't mean that encryption is disabled. It just means it's optional. I'm building an XML packet here. Messages don't have to be XML. They can be XML. They can be just straight binary data. They can be a text blob. XML is the de facto standard because it's easier to query and use. And then basically, the next thing that I'm going to do here is send that message to my server. The way I do that is through some new DML called, you can see on the bottom there, send on conversation, message type, inventory update, and then my payload, which is that message variable that I defined right here. So you can think of a send similar to an insert if you correlate it to your typical database usages. So I'm going to run that. And what you should see is, since these are on the local instance, notice here what I'm going to do is query my server queue. You can see that a message has been delivered to my server queue. I'm casting the body of it as XML, and if I click on it and look at it, you can see it's that payload that I had built and delivered earlier. The next thing I'm going to do is, as the server, I'm going to pretend that I'm the server now, and what I'm going to do is receive that message off the queue and do some processing. And basically what I'm going to do here, you can see here's my receive. Think of a receive as similar to a select. The difference is that a receive would be actually closer similar to a select and then a delete. So if you receive off a queue, you're pulling a message off. So you're not only reading that message, you're actually pulling it off for processing, so it's going to be gone off the queue. So think of it as a select and a delete all in one thing. It looks like what I'm going to do is shove that data into a temporary table and then just show the data that I pulled off the queue. So you can see here in my receive statement, what I'm doing is pulling the conversation handle, the message type name, and the body of the message into 3 different local variables. Oops. So if I run that, and I'm actually going to run this right to the, notice I've got a commit transaction there that I don't have highlighted. I'm going to run this through the commit. But now I started the transaction, I haven't committed it yet. Now you can see that I did pull this message off. If I click on the XML, it's the same payload that I received before. And what I would do is if I query my temp table, I should see it there as well. Okay? Now if I decide at this point to roll back my transaction, before I do that, let me do a quick query of the server queue to show you that it's not there. If I query my server queue, you can see that message is now gone, okay, because that receive pulled the message off. But if I roll back my transaction, what should happen? You notice that I don't any longer have that temporary table because I actually created that temp table in context of my transaction. And if I come up and query my queue, that message should be back on my server queue for processing. So your receiving and sending on a queue is fully transactional in terms of being able to receive, process, and commit. This time I'm going to do the same thing, only I'm going to actually commit it. I should now see it in my temporary table for holding. And if I query my server queue, it should be gone, and it is. Okay, so the next thing that I would logically do is, as the server, I would process that data and I would send back some sort of response. Okay? So what it looks like I'm going to do here is I'm going to take that message packet that was delivered. I'm going to find out what the quantity was in the product. I'll show what it is, what I pulled out of the message. I'll show what exists in my inventory table for that product. And then what I'm going to do is update my inventory table to now have a quantity equal to what the quantity is plus the data that was sent. So instead of changing the quantity to 3, it looks like what I'm doing is incrementing the quantity by 3. So that the quantity for that title or for that product should go from 200 to 203. Okay? Then I'm going to show you the after result for that product. And I'm going to formulate a response to send back to the client. And what that response is going to say is that this product was requested to update, to this value, and the new quantity for that product is this. So my response should look like title ID of PS 1783 or whatever that was. My quantity update requested should be a value of 3, and my updated quantity should be 203. Then you can see what I'm going to do is, again, send a message. This time it's going to be of type inventory update response, because this is the server responding back to the client. Now again, the client is obviously not waiting around doing anything. The cash register has gone off and is processing other people. And I'm going to send a payload of that response that I formulated. Then I'm going to end my conversation and commit. So if I run that all in one big statement, what you can see is that here's the payload, the actual data that I pulled off for processing. You can see it's the same payload from before. Before I ran the update, this is the values in the inventory table. After I ran the update, these were the values. So you can see that worked as I expected. Now if I query my client queue, I'm going to query my client queue again. And I see 2 messages. The first message is the inventory update response that I formulated and sent back to the client. You can see that it looks the way I expected it to look. The other one is what's referred to as an end dialog message. So the way that dialogues or conversations are terminated is by sending a message back and forth between the 2 systems to say, I'm done on my end. You've got everything from me that you're going to get. So I'll send you a message saying I'm all done. And when you receive that message, you should clean up on your end too. So that's the way you actually clean up or destroy an actual message conversation. Now what I'm going to do is, on the client end, I'm going to mimic actually the client processing that response. What I'm going to do is, in a simple loop here, I'm going to continue to receive from my queue until I don't have any data left. I'm going to receive the top one. I'm going to pull off the message type and the actual payload. If this is that end dialog type message that I told you about, I'm going to clean up on my end, and then all I'm going to do is print out a simple display of what it was. So if I run this, I should see 2 printout messages, one saying I received my update response, and one saying I received my end dialog. Okay, the next very simple demo that I'll show you will be related to HTTP endpoints for SQL Server 2005. So I'm going to show you here, is I'm going to quickly create a connection. Oop, put the right password. And I'm going to use my AdventureWorks database here. I'm going to create a simple function that does nothing but take account of this table where the employee ID equals the parameter that's passed in. Okay? Oops. So I'm going to create that. The next thing I'm going to do is reserve my namespace. So this is what I was telling you about, where you reserve a port in a namespace through the HTTP sys. That's exposed through a stored procedure that you can see here. I'm going to do that. And what that's going to do is reserve port 80 on my machine in the ADV end namespace for use with SQL Server. Above, I'm going to use integrated authentication, clear ports. I could use SSL ports here instead of clear. I'm going to define this for SOAP. You can see what I'm going to do is define a web method called getEmployeeOrderCount. And that web method should execute this function, employee order count, that I created above. So if I run all those, okay, that's fine. What the function would return is, I'm just going to run the simple function here in T-SQL. You can see that I should get, if I use the parameter 231, employee ID 231, I should get a count for 362. So if I come out to a .NET app that I've created, very simple .NET app, that does nothing, but it has a simple form where I put in an employee ID and hit go. And once I hit go, all it's going to do is connect to this web service using these credentials. And then what it's going to do is actually fire, you can see right here, this getEmployeeOrderCount web method. Okay, and it's going to pass, whatever value I put in that text box as a parameter. So if I fire this up and use the same employee ID as I did over here, which is 231, and hit go, you can see that I get a simple message box that says I got 362 employees for that, records for that particular employee ID. And that was using HTTP, not your standard, T-SQL, ADO.NET type connectivity to your database. Okay, so that's about, I think we got about 2 minutes left. Let me put this slide back up. Any questions? I don't see any. Yep, got one there, I think. It's hard for me to see up here. So. Mm-hmm. Okay, so you have a single database and a single system, and you want to scale out using Service Broker. You have web servers connected to SQL. And your web servers do something like process client requests or something that could be done asynchronously. Okay, so how would you do that? Well, the most common way to do this would be your back-end server would be your server, your target, okay? And your web front-end servers, I don't know how many, say you have 10 web servers, how many you have. The standard, or the most common approach would be to install SQL Express, which is probably already on each of your web servers, and have your web front-end code, instead of connecting to your back-end server, connect to the local SQL Express instance, execute a procedure that sends, like you saw on this sample there, sends on that, you configure your dialog and whatever, and it basically wraps all your parameters up in an XML payload or something and sends that message. What will happen is that message will stay on your SQL Express instance for anywhere from 1 millisecond to 100 days, depending on the availability of your backend server. And that message will get delivered from your Express instance on your front end to your backend server, where you would have a procedure or something that was auto-activated that would pull those messages off and process them. And then you could optionally send back a response. It sounds like it's probably not the type, it's a one-way communication most likely. So that's your standard. That gives you a lot of different things. You scale out capacity, so your web servers, you can add web servers as you need to. You could also add an additional back-end database system if that back-end server eventually started getting overloaded. One additional benefit is it gives you some additional availability. So if your back-end server goes offline, your front-end clients would never know about it, because they would connect to that web server, they would enter their request, hit go, and that message would still be delivered, they'd still get a successful confirmation, and that message will just reside on that SQL Express instance until your backend server, either if it's clustered, maybe it'll fail over and come up another 2 minutes later, if you have to do a restore from a backup or whatever. As soon as you bring that up, I do have a demo that we didn't get time for that would show you if you did like a backup restore or if a service went offline. As soon as that service comes back online, within about 1.5 to 2 minutes, those messages will all be delivered, processed, and all is well. So it gives you some additional buffer for availability as well. So that's your standard model you'd use there. Good question. Okay, any others? Okay, thank you very much.